hack videos almost never explain how things are supposed to work, and the few that do never test it properly. But in this channel, we're about learning new skills and using science, so we have to change that. I've selected 3 impressive hacks to analyze and test. The first one should help you buy the best drinks to cool without compromises. The second one claims to cool ice and water even in direct sunlight. And the third one should make drinks colder without ice or freezers or anything like that. We will explain what's the science behind each hack and test them to see how well they work, if at all. So hit the subscribe button if you don't want to miss any episodes of this series. But before we do any of that, we need to understand the science of cooling. For example, have you ever wondered why we use water to cool metal and not the other way around? To explain this, we need thermodynamics. I know thermodynamics is a very hard subject, but if we don't care about the small details, we can make it almost intuitive. When we're cooling something, we are taking its thermal energy and moving it somewhere else. How fast we can do that depends on mainly 3 factors. Heat capacity, which is the amount of energy it takes to change the temperature of a substance. The temperature difference between the drink I want to cool and the environment I'm going to cool it in, so like the fridge. The third factor is the heat transfer coefficient, or how fast the energy can move from our drink to the environment. To make everything more intuitive and avoid any casualties, I've prepared this contraption here. So this represents the cooling process of any material. We have 2 containers connected by a pipe. Each container represents one of the 2 items, so either the drink that we want to cool or the environment where we're going to cool that drink. The liquid inside of the drinks represents the thermal energy, so a higher level of liquid represents a higher temperature. In this case, we would have a very hot drink, for example, and this would represent something very cold, like an ice bath or a fridge. The next thing we have to look at is the area as seen from above. That would represent the heat capacity, so this would mean a small heat capacity, something like metal or stones, while this represents something with a higher heat capacity, something like water or ice. Finally, the third factor to look at in our model is the 2 connecting pipes. They represent the thermal transfer coefficient, or how fast can the liquid in our model and the thermal energy in reality, how fast can it flow from one to the other. I know you might be even more confused than before, but do not worry, everything gets easier from now, you'll see. And we can go step by step, starting with heat capacity, which is generally what trips people over, but in this model is very intuitive. You might have heard of thermal capacity, heat capacity, or specific heat. These are all very similar variables related to each other, and they all tell the same tale. Some materials take a lot of energy to change temperature, and some take very little. In our model, this container has a large area, so it represents something with a large heat capacity, like water. This other container has a smaller area, and it represents something with a smaller heat capacity, something like metal, for example. So when we put a hot piece of metal into cold water, you can see how the liquid starts flowing. They will both end up at the same temperature because of the second law of thermodynamics. That means the same level of liquid. But the final temperature, the final level, it's much closer to the water than the metal. That's because water has a higher heat capacity, it takes more liquid to fill the container, it takes more energy to raise the temperature of water compared to raising the temperature of metal. So ideally, we would want our cold environment to have a greater heat capacity than our drink. The next piece of the puzzle is temperature difference. When we put a warm drink into a cold environment like the fridge, the speed at which the drink cools down depends on the difference in temperature between the fridge and the drink. That means that it's faster to cool your tea from 100 degrees to 30 degrees by putting it outside the window in a cold winter day compared to doing it on a summer night. No shit, Sherlock. I know it's obvious, but it doesn't make it less useful. You can also see this in our model, as the first part of the container drains faster than the second part. However, the biggest factor for the speed of the liquid moving across containers in our model is the diameter of the pipes, and that represents the last piece of our puzzle, heat conductivity. Just like with heat capacity, there are several variables we could look at. There is heat transfer coefficient, thermal conductivity, but the takeaway is one. Different materials transfer thermal energy at different speeds. Metal, for example, is really good at transporting energy quickly, which in our model corresponds to a fat pipe. That's the reason they are used to cool computers. Insulating thermos, however, use glass and vacuum, as it almost stops any heat moving across, equivalent to having a very tiny pipe in our model. So yeah, we should try not to use plastic, prefer metal, and definitely never use glass if we can. So let's recap. For the best cooling possible, we want our environment to have a higher heat capacity than the drink. If possible, that's not always easy. Then we want it to have a much lower temperature than the drink, because that guarantees a lower equilibrium temperature and it guarantees a faster cool down of the drink. And then finally, to make sure that the drink cools as fast as possible, we want to use the fat pipe and not the thin pipe, so that we don't have to wait around for it's moving.
One eternity later.
At this point, you should know enough about cooling to guess which hacks will work and which ones will not. So leave a comment with your predictions below, and I will see you in the next video when we compare metal and glass to see which one helps cool our drink faster. Until then, remember to subscribe to the channel so you don't miss the video, and I will see you soon. Have a nice day. Bye! How fast this happens depends surface area.